Let's have a look at Le Chatelier's principle in a bit more detail and the factors that affect equilibrium. So we know when equilibrium is established and then a change in the system occurs, the equilibrium, the reversible reaction, will respond in such a way as to counter that change. So we know that concentration, pressure, and temperature are the three factors that affect an equilibrium. Catalysts do not affect the position of equilibrium. However, we know that catalysts decrease the activation energy and thereby reduce reaction rate. So it just reduces the time that it takes to get to equilibrium. But the same equilibrium will still be established with or without the catalyst. So changes in concentration. How do changes in concentration occur? If we talk about solids and pure liquids, we actually can't change their concentration. So we say they have a concentration of 1, being that if we talk about concentration, which is equal to number of moles over volume, as soon as you increase the number of moles of a solid or a liquid, then you're also increasing the volume in proportion. Okay, so concentration is only really in reference to gases or aqueous substances. So concentration can be increased by adding more of the reactants or more of the products of the gas and the aqueous substances within that particular equation. The concentration can be decreased by removing reactants or products. Alternatively, if you have an aqueous solution, then that's going to decrease the concentration of the substance dissolved. Okay, adding a substance favors the reaction that uses it up. So what does that mean? If we add a reactant, the reaction that's going to be favored is that which moves towards the product. So we should have more products being produced. If we increase the concentration of a product, then likewise we're going to have an increase. Then we're going to have a subsequent increase in the concentration of the reactants because the reaction will favor that particular direction from products to reactants. Removing a substance favors the reaction which produces it. Okay, so it doesn't matter if it's in, if you like, the forward or the reverse reaction, that's what's going to happen. So you can have a read through the table, and that summarizes what we've just spoken about, the addition of reactant or product or the removal of reactant or product. So how does this relate to collision theory? As the concentration of a reactant is increased, the frequency of successful collisions of the reactant would increase also. So then it makes sense, if there's more reactant present in the system, they're going to collide successfully, therefore they're going to generate product. How do we see this in graphical form? What we generally tend to see is concentration either increase or decrease of one particular substance. Okay, because you're not going to increase the concentration of all of the reactants at once or all of the products at once. So we generally tend to see an increase in one substance. So if we say A is the red and B is the blue, you can see initially the system is at equilibrium, the concentration is not changing. At a certain point in time, the concentration of A increases significantly. Okay, so let's say we've added more reactant and the system is going to adjust itself now. So that means that more of B will be produced because A is going to be colliding with itself producing B. So you can see A is slowly decreasing in concentration, okay, as all those A's collide and form B, and B is slowly increasing as it gets formed until their concentrations remain constant again, a new equilibrium is reached. Now, when we talk about changes in pressure, we're talking about changes in gas pressure. So gases are what we really need to look out for in our equations. So if we're discussing the first example, then you've got 2 moles of nitrogen monoxide and 1 mole of oxygen forming 2 moles of nitrogen dioxide. They're all gases, so they're all relevant. If we're talking about photosynthesis, only the carbon dioxide reactant and the oxygen product are going to be affected by pressure. And then likewise, in the third example, only the oxygen gas will be affected by a change in pressure. So how do we increase pressure, decrease it? To increase it, we can add more of the gas involved, or we can decrease the volume of the system. That means we're bringing those gas particles closer together, so we're increasing the pressure. We can decrease the pressure by removing some of that particular gas involved, or we can give more space to that particular system, increase its volume. That means the gas particles will be further apart, therefore the pressure will be decreased. Okay, the effect of a change in pressure has on an equilibrium system is determined by the number of gas molecules or moles of gas on either side of the equation. So what does that mean? When we increase pressure, okay, so the gaseous molecules will be closer together, the equilibrium will shift to the reaction which has less gaseous molecules or moles of gas, okay, to alleviate some of that pressure. When we decrease the pressure, okay, or we give the container more space, the reaction will shift, or the equilibrium will shift to the side with more moles of gas to re-establish a little bit of a higher pressure. How do we see pressure on a graph? Now, we're seeing both the concentration of A and B rise. Remember, A is the red, B is the blue. Okay, if we're talking about whether or not these two are gases, they've both been affected in this particular instance. The increase has been for both A and B. So therefore, we can see there's been an increase in pressure, because an increase in pressure is going to cause an increase in concentration. Likewise, a decrease in pressure, you're going to see the graphs decrease, okay, instead of the lines going vertically up. And then what we can see is a slow readjustment of that equilibrium. And lastly, changes in temperature. So if we had another equation now, A plus B gives us C, and we know that that's exothermic, then we know C forming A plus B, the reverse reaction, is endothermic. Or, as you can see, it's represented with the reversible arrows, exothermic and endothermic at the bottom there. If you're given a delta H, and that's got a positive or a negative sign, that's only in reference to the forward reaction. So in this particular instance, because it's exothermic, the delta H would be negative in some form, some value of kilojoules per mole. Okay, if we increase the temperature, then we're adding heat to the system. Okay, so the system is going to favor the endothermic reaction, because the endothermic reaction is going to use that heat up. Okay, it's not going to produce more of it, it's going to use it up. Conversely, if we decrease the temperature, we're taking heat away from the system. That's going to favor the exothermic reaction, because the exothermic reaction is going to release more heat. Okay, how do we see temperature on a graph? If we're having a look here, then the equilibrium has already been established, okay, from time 0 to a certain point in time, and the temperature change is shown by a gradual change in the concentration of the substances, because there's not a sudden increase in concentration in one or the other. Okay, the addition of heat occurs slowly over a given period of time, and the equilibrium system adjusts itself accordingly. And that brings us to the end of the three factors that affect equilibrium, okay, and how they react using Chatellier's principle, that they counteract the change. What I'm going to do is I'm going to leave you some examples up on the classroom and their worked answers to help you to get that done.